So welcome to the Machine Intelligence session of ESEC 2019. My name is Sandra, and I am a second-year engineering science student. And today I get the opportunity to introduce you to someone who's redefining what it means to be an engineer, breaking down the barriers between science and art, and taking the time to think critically of the true powers and dangers of artificial intelligence. Our speaker today is Xavier Snelgrove, an engineering science graduate of the electrical and computer engineering option, who is every part the engineer, artist, computer scientist, and teacher we need to help guide us into a conscious machine age. After graduating from U of T in 2011, Xavier went on to co-found Whirlscape and create Minium and Dango, products that make use of neural nets to better the experience of mobile keyboards. Throughout his career, Xavier continued to take on diverse opportunities, including working as a developer at KPIC, a researcher at Disney, and currently at Element AI doing applied research. On top of all that, Xavier has been keen to show the world the beauty and creativity of code, organizing events, talks, and showcasing his own creations to teach others how code can be made into art. However, aside from the art that he can create from his algorithms, Xavier is no stranger to the societal and ethical implications of machine intelligence. In his talk today, he will discuss the ups and downs, the beauties and the beasts, and the best and worst to come with machine intelligence and how we can be smart in our shift towards AI. Please join me in welcoming Xavier Snelgrove to the stage.
Just a sec, let me get set up here. Wow, that was a great intro, thank you. It's a lot to live up to. I often get nervous, especially now. I've been feeling that engineers more and more need to talk about these sort of ethical and societal questions, but there's a lot of imposter syndrome when you do that, because as soon as you start to raise those questions, it's like, well, am I a good standard? Am I doing these things that I need to be doing? So it's a big honor to be here. I'd like to take, if possible, a selfie, because this is where I went to school. So if I could just get this up. All right, everyone smile. Awesome. Okay, cool. So hello, I'm Xavier, and so yeah, I'll be talking again about the creative potential and societal risk of applied machine learning. In this talk, I'm going to try to talk both about my own career a little bit, which I think I think every career is an unusual path. So I think every story you hear about one, you hear another unusual path, and I think as a reminder that there isn't one right way to do things. I'll talk a little bit about like an intro to like the most basic intro to what machine learning might be, to make sure that we're on the same page. And I'll share some of the risks and challenges that I see with machine learning and some of the struggles I've had in my career about learning to recognize these risks. And then we'll also get into my creative practice as well, because I think it's a fun way to see some of the different things you can do with these technologies. So first of all, I'm a relatively recent grad, I think, of ESEC. So I was 1 TO plus PEY. There I am with my Aero 201 robot, Mr. Roboto, which was, I had to test light up balls to see if they light up. I don't know what people do today, and you know, there's dubious fashion choices, which I still make, but I recommend you button up your shirt in your career as engineers. So I was the last comp option of ESEC. So I didn't do the machine intelligence option, it didn't exist. But I wanted to do an option. I was happy to get the broad base that I'd gotten from engineering science. But a lot of my passions tended towards the programming, the computer science end of things. And so I chose to do the comp option. I was the very last person in the option before they removed it. And I think that it seemed like the machine intelligence option is probably one of like the natural successors of that concept, where you're moving a little bit more into the abstract, but as I think we'll see in this talk, it's not as abstract as I may have originally thought. So I did that. I graduated ESEC. And then I wasn't quite sure what to do next, and I started a master's in computer science here in computational photography. So I was doing a lot of work there in sort of signal processing, image processing, and trying to see if we could design new cameras that were better able to capture things like depth in the world with new lens designs. So this is this field that's all about the question of, now that we have computers attached to phones, what are the things that we can do differently? Again, this was not that long ago, but it was long enough ago that this was before there was as much computation built into the photo apps that we have in our phones today. But a lot of the things that we see about like HDR and like face detection and like combining multiple photos to make sure everybody is smiling, those are the kinds of problems that were worked on in that field. But I was always not the most focused person. I was always working on multiple things. And among other things, I was helping out a friend with his research on the side. So here I am in science mode, doing some science. And so I had a friend who was taking the human-computer interaction course in his master's. And he started to look at the question about how could we sight-free type on mobile devices that have no tactile feedback. And so this was like this kind of researchy question that was posed as the class, and he had this crazy idea of like using the accelerometer on the phone, and what if you could put the alphabet like up in the sky and then point the phone in different directions, and like, you know, Q would be over here and, you know, P would be over here on a QWERTY keyboard. And he was building all these things, but very much from the user interaction side of things. And I came in and helped him with the statistics of language modeling, and this question of, okay, if we want people to be able to type quickly in this way, we're going to have to expect that there'll be a certain amount of noise in the inputs that we see. People will tend to miss the letter that they want, but if we have a strong prior that they're writing in English or in whatever language that we've trained it on, then we can help do the autocorrect in that. So we started doing this. First, this was like a research project he was doing, but then he got some funding from what at the time was called UTest, I think may still be, which is a program at U of T for trying to commercialize research. So we got a small amount of funding to see, hey, can I try to turn this into a startup? And you know, I was still helping him out, but I was doing my master's and just kind of helping him with the algorithms, helping him build the first version of what ultimately became an app. So he started with this, you know, point in space thing, but it turned out that that was probably a little bit esoteric for what people would actually want to do to type. But we realized that those same algorithms could allow you to type in much smaller contexts. So we ended up designing this like one-row keyboard that would take up very, very little of your screen space, so you could have the rest of your screen for the other things that you might want. So we built the first version of this app. We ended up launching this crowdfunding campaign where, because I was doing camera research, I had access to all these really nice cameras. So like after hours in the lab, we like filmed the crowdfunding video with these nice cameras, explaining how this thing would work. There's a very cheesy like infomercial style video on YouTube, which you can watch, which I'm not gonna expose you to here. We launched this crowdfunding campaign, and our goal was to raise $10,000. You know, it was just like, we kind of wanted to check if this was something that people would be excited by, something that people would want. And our plan was, you know, we're going to put this out, and then we're going to spend the month of the campaign, actually I forget now if it was 1 month or 2, but we're going to spend that time running around, you know, on the phone with every reporter we could get our hands on, giving talks, trying to build interest in this thing. So we launched the campaign, we sent out a press release, and then we hit our $10,000 goal in 6 hours. And so suddenly the entire plan changed, right? We had this thing, we thought maybe people would be excited by it, and it turned out that everybody hated, at that time, the experience of typing on their smartphone. So even just the promise of it being better, at that point we hadn't even launched something, people were really, really excited by. And so, you know, we raised the goal in 6 hours. Instead of us having to go out and like do a road show of trying to help get people to pay attention, we were getting constant calls from reporters, and we had all this coverage, it was very exciting. And I was put in this kind of weird position. I hadn't finished my master's yet. And there was this project I was kind of doing on the side. I told my friend, you know, I'm helping you out, but like this is kind of your thing, and I'm gonna do my thing. But now I had all this momentum behind a project that I was working on, and I had to make a choice. And the choice I ended up making was to leave the master's and join as like the co-founder and CTO of WorldScape to pursue this. Which I'm not saying you should drop out of your master's or to school, but it was an interesting path to take, and it means I don't have a master's now. So we did this for a while. So after all of that energy, you know, we kind of launched the project. At the time, we thought, you know, $90,000. Wow, this is like the most money I've ever heard of. Like, you know, I can retire now. I'm going to go hang out on the beach. Like, we honestly thought we were the world's most successful entrepreneurs at this point. So then we operated the company for a little while afterwards, thinking, oh, you know, we launched the product, we launched it on time, which is like unheard of for a crowdfunding campaign. We had all these users using it, we were fixing all the bugs, people seemed to like it. But we kind of stagnated and didn't really realize that we were stagnating. We stopped kind of growing. We weren't really trying to innovate on the next feature of the app. We were just we put out a thing that we were happy with and we thought we were done. And as we were sitting around, some more people had joined the organization, and we were encouraged to apply to Y Combinator, which actually dovetails with the talk yesterday. And for us, that was a very important for the business experience of having a very different business ambition mindset. We got down there and suddenly it was like growth. You have to focus on growing your product. So we went down to Y Combinator. We ended up raising at the time like a seed round of $500K, which gave us like more time to like grow the company a little bit. We always stayed relatively lean. And we moved down to California for a few months to work on this project. So this was a really interesting experience. I was dropped in with a whole bunch of other startups at kind of a similar phase. Suddenly I had a very different new peer group that were dealing with very different kinds of problems. I think I learned a lot in that context, and I'm really happy for the experience. There were questions, and we'll come back to some of these again, but one thing that sometimes bugged me there is in the context of these sorts of business accelerators, almost the work that you're doing becomes secondary to the structure of the work. And what I mean to say by that is the program very much focused on pick a metric that reflects the health of your business, and your goal should be to grow that metric. And if it involves changing what you're doing or continually adapting, as long as you end up growing that metric, that is a sign of success. That is a good way to grow a metric. But I think some of the interesting challenges we're seeing now, especially in the technology industry, are a result of that ethic taken a little bit too far. And this idea of like the only thing that matters is growing. We'll talk a bit more about that throughout this talk. Anyway, so we did that. We ended up launching, we made some bets that may have been incorrect. We thought smartwatches were going to be, everybody was going to wear a smartwatch, and we showed that our technology could let you type on a 1-inch screen, and we had all these like smartwatch versions of the keyboard. Turns out smartwatches didn't turn into the market we thought it was going to be. We ended up launching a second product based on one of the most popular features of the keyboard, which was we'd launched our keyboard around the same time that emoji came to the West. And there were really bad emoji tools at the time. So in our keyboard, at one point, we put in just a very simple predictive emoji feature that, like, if you type the word pizza, pizza would come up, like the most rudimentary thing you could imagine. But very quickly, it was one of our most popular features by far. And so we ended up creating a standalone product that was just that. And so we really upped the ante on what the algorithms that we could do, where we ended up training what's called a recurrent neural network on huge amounts of natural language with emoji associated, scraped from the internet, places like Twitter. And we built this algorithm that used deep learning to understand what you were talking about. Understand is a stretch, but to see patterns of what you were talking about and figure out emoji that were relevant to that statement. I learned a lot about this thing that I had known nothing about before at the time. Emoji is a very weird, complicated, interesting technical subject, as it turns out. There's all these strange international committees deciding what concepts and symbols are significant enough to be introduced into the standard. This is a visualization of sort of a byproduct of what we'd end up learning. As part of how this neural network worked, and I'll talk a little bit more about these ideas later, it had to learn a vector representation of every emoji. It had to learn some sort of a point in a high-dimensional space where each emoji would lie. And then the sentence that you typed would also get embedded into that high-dimensional space. That's sort of how the structure of this neural network worked. And so the emoji that were relevant to your phrase were the emoji that were, in some sense, closest in this high-dimensional space to the phrase that you had typed. So now, as part of training this network, now each of these things that I have, each of these emoji, has a vector associated with it. And so here I'm visualizing it with a technique called t-SNE, which is quite popular for visualizing these kinds of embeddings, which tries to take this high-dimensional embedding and bring it down into, in this case, 2 dimensions in such a way that things that were close together in the high-dimensional space tend to be close together in the low-dimensional space. Now, in general, this is impossible. This isn't going to capture all the relations that exist in that high-dimensional space, but it gives you some sort of a sense. Fortunately, this is a low-resolution projection, so you can't really see. But you end up getting kind of all the happy faces clustered together, all the sad faces clustered together. It figures out the different foods are similar to each other. It figures out things about the astrological symbols. And this is purely based on how people use these things in the wild. It's figured out that different smiley faces mean similar things because they're used in similar contexts. So I didn't tell it anything about them being smiley faces. This is learned from the data. And that's the kind of thing that comes out from machine learning, that you show it a huge number of examples of how things exist in the world, and it finds patterns within those. So we did that for a bit. We had some goals to have hundreds of millions of users. These products were both like relatively successful, I would say. but in the scope of internet businesses, probably not to the scale that we needed them to be. So Minuum, our keyboard, I'm not sure since I've been gone, but definitely still has thousands, probably tens of thousands of daily active users still who are very happy to use it as their daily keyboard, but it's not the hundreds of millions to billions of users that sustain a lot of the internet companies that we see. And Dango similarly was actually our best reviewed product. People like it a lot. I'm not sure what the active users are there. But we realized that this consumer growth route that we'd gone, that we kind of pivoted to with our investor funding, where the concept was this is really what we should focus on, is getting user growth and then the money will follow. We ended up getting to a point where we weren't hitting that growth that we were targeting, and we started trying to see what else we could do with these things that we'd built. And it turned out that there was a market for the core technologies that had gone into building this emoji predictor. So this emoji predictor, in order to work, had to be able to understand a lot about text. It had to understand the emotional content of text. Is this happy? Is this sad? As well as some of the semantic content of is this talking about pizza? Is this talking about Christmas? Whatever. That core tech turns out to be useful in other contexts where you might want to search based on the effective content of text, or maybe other contexts where you'd want to do emoji prediction. So we ended up licensing this technology to a number of different organizations. And actually, for the first time, our company became profitable and sustainable. That was really cool. But we weren't necessarily always building new algorithms or designing that new thing. And I was kind of the tech guy. I always wanted to be doing the research and figuring out something else we can build. So I decided to move on. So I started consulting for a little while. I consulted with a number of small and mid-sized companies, helping them figure out how to work with AI, how to hire AI talent, that kind of thing. That was interesting. I learned a lot. I learned a lot in all of these processes. I wouldn't do it differently. But I started to feel relatively isolated, always being the tech guy in the room, going into a consulting engagement where I'm the only person who knows about the topic I'm talking about, realizing that nobody can hold me to account for the caliber of my ideas because I'm there to tell them the ideas. And so I wanted to put myself into a context, again, where I'd be challenged by my peers. And I decided to try joining a larger organization. I mean, it's still a startup, but I joined a company called Element AI about a year ago. And I'm an applied research scientist now at Element, working on a question called AI explainability. I'm not going to get too much into that here, but it's this question of, great, this neural network is good at figuring out that you're happy or sad, but what signals is it looking for? How is it working? How does it figure out if you're happy or sad? And this is a big open research question. How do we explain what the algorithm is doing? And it turns out a lot of consumers of AI products want that. And it's an important question, and it's an interesting scientific question as well. So that's what I'm working on now. So that's kind of a broad arc of the small number of, again, I graduated relatively recently, but this is my career to this point. Relatively entrepreneurial, relatively self-directed. But one of the things that threw me is that, in my engineering training, and my understanding is actually, I was talking to some students yesterday, this may be changing a little bit in the program, but I was really well prepared for the math that I face in the problems that I'm solving. The math of a lot of machine learning is way simpler than most of the math that you're learning today at EngSci. I never really have to solve an integral. There's people who are trying to do these things to make proofs about the convergence of these networks and all kinds of things. But the base math that you need to engineer a modern deep learning system is actually relatively simple. You need the chain rule and you need matrix multiplication, and that's pretty much it. And then it's a whole lot of empirical things that people have learned and tricks of the trade. So I was very much prepared for that by engineering science. I was ready to go. I had all the signal processing stuff that I needed. I had all the linear algebra that I needed. But I started to realize that there was something that I hadn't learned so much. So does anyone recognize this image? Has this been shared with you before? Who recognizes this image? All right, about half the class. So this is the bridge in Quebec that apocryphally is what the Iron Ring is cut from. So the idea of the story of the Iron Ring and the Iron Ring ceremony is all about trying to tell us our responsibility as engineers, right? It's this question of, here the engineers failed to design the bridge properly, and then the bridge collapsed, and a number of people died, and this is a reminder of our important what's the word I'm looking for? The noble pursuit of engineering and the importance of that. But I did the Iron Ring ceremony. I'd been in the computer science option. I was happy to do it. I felt like I want to be a responsible member of society. I want to be a good person. But it felt very detached from the kind of work I was doing. I was like, well, In some contexts, possibly I'll be doing computer science for like an airplane control system or something. But I use all these apps. There's all these things that like I enjoy using that like make my life better, whatever. Where if it crashes, it's not the end of the world. So it felt there was this like detachment between the responsibility I was being told that I had and the career that I thought I was going on. So I was happy to do the ceremony and all these things, but it felt like there was no connection between that and the work I was going to be doing. Now I think myself and actually the culture generally is starting to reevaluate our relationship with computer science, with tech, and with tech companies, and starting to realize that actually we are building really, really critical infrastructure. It's not as obvious as a bridge falling down, though. We're building like the infrastructure on which like society and friendships and humans operate, right? Most communication that people now do is mediated by something that is built by somebody like me. And I think we're only just starting to realize, I mean, a number of people have been raising alarm for a long time. I'm starting to realize, and I think as a broader society, we're starting to realize the responsibility of that, and I think it's a different framing. So in recent years, there's a lot of blowback about Facebook checking to what extent they could manipulate you, make you happier or sadder based on the kinds of posts that they would show you without informed consent. Then they leaked huge numbers of profiles. They arguably affected the democratic process in major countries. This concept of addiction to technology is becoming very, very mainstream. We're starting to realize that these phones that we rely on are almost in an adversarial relationship with us because very growth-oriented people like myself and people who are thinking about how do I optimize, how do I increase the number of eyeball hours spent on this app are finding all kinds of tricks to pull us in and make us spend more and more and more time without necessarily reflecting on why we're doing that or whether or not it's actually good if we spend more time on Facebook. There's groups starting to call out the fact that in many cases, the algorithms that we're doing, and I'll talk more about this later, are reinforcing racism or reinforcing other structural problems of our society, especially when you train them on historical data of our society, then they just reflect that historical data forward. And if there's ways we're trying to move forward as a society, just reflecting back our history isn't necessarily the best way to do that. Facebook has been linked to genocide, as has WhatsApp, as has Google, as has a number of these organizations. Amazon started using AI to screen resumes, and it turned out that it was very explicitly discriminating against women. Self-driving cars, for all their promise, are still large lethal weapons that are driving around, and so this is still something we have to be very conscious of. So I realized that my experience of engineering had not necessarily prepared me to start thinking about these questions. So a big challenge I've had for the last few years is trying to find ways to think critically about these things, to read up on these things separate from the education that I had. And I'm trying to look for the right voices, and I'm still searching, but I'll share some examples of places where I've seen people really critically digging into these questions. And I think it would behoove you all to look for similar things. Okay, so engineering will teach you the math that you need. As I mentioned, I learned the math that I needed at EngSci, but not necessarily the social things. That said, for this talk, let's look briefly at some of the math at a very high level, just so we're all on the same page about kind of what we're talking about. So, what is machine learning? I'm talking about machine learning here much more than I'm talking about AI. Nowadays, these terms are almost used interchangeably in the popular culture because a lot of the big breakthroughs have been in the field of machine learning recently that have led to a lot of the hype and a lot of the attention on the field right now. I very much work in machine learning. That's really where my expertise is. That's what I'll be talking about here. There's lots of subparts to this, but at its simplest, the idea is instead of explicitly writing out some function that I'm trying to create and saying, here's the algorithm, here's the recipe, do this, then do this, then do this, instead, I'm going to use examples to define the function. I'm going to say, here's a bunch, I'm trying to learn a function that maps x to y. Here's a bunch of examples of x's and y's. What should the function be? That really, in a nutshell, I mean, that's a subset of machine learning called supervised learning. That's a big chunk of the reality of the work that we do. So what might that look like? So let's say I have measurements of the width and height of fruits, and I want to figure out if they're lemons or oranges. This is a very exciting problem. I want an algorithm to do that. So maybe what I should do is go to the supermarket, buy a whole bunch of fruits, and measure their widths and heights. So this is an actual data set that this guy, Ian Murray, who is at, I think UCL. I'm not sure what university, but he actually went out and gathered this data set. So here, all of the orange X's are oranges, and all the blue circles are lemons. And you can see there's this width and height. And I want to write an algorithm to say if something is an orange or a lemon. So you could probably do this by inspection. You could look at this and you could say, oh, you know what it looks like? If I draw a line here, that does a pretty good job separating these two classes. It puts the lemons on one side and the oranges on the other side. You know, there's one orange on the wrong side here, so maybe there'd be a small amount of error. This might be a pretty decent first approximation of how this would work. So you could imagine writing a function. So my understanding is a bunch of you have done Python, so this is some Python, sort of. This would be a function that tries to figure out what the fruit type is. So its input is the width and height. And what it's going to do, that equation on the second line is the implicit function of a line. So I'm saying that there's some value z, which is going to be some coefficient times the width, plus some coefficient times the height, plus some final coefficient. And that would define an equation of a line. The level set where that is equal to 0 would be that red dotted line there. And then everything on one side of that line would be positive. Everything on the other side of that line would be negative. So if I knew the values of p0, p1, and p2, then this function, I could implement this concept of figuring out what side of a line something is on. Very simple. Now, in the context of machine learning, the way we'll do that is we'll try to minimize some objective function. So in most machine learning problems that people tackle, one of the challenges you have to do is find some way of defining a loss function or objective function that is minimized when you have the right solution. And so in this case, I would like some numerical way of saying how much are my data points on the right side of the line? How often are they on the right side? How often are they on the wrong side? And how, ideally, they're as far away as possible from the lines. They're not near the border. I'm going to show the math here. Don't bother learning it. This is a very popular kind of classification algorithm. It's called logistic regression. This would be the particular loss function you would use. So I'd have that z that I calculated. So it's positive on one side of the line, negative on the other. I would pass it through this logistic function, which would make it instead range from 0 to 1. I would define my loss function as a sum across all of my data points of the value on the logistic. If it's a lemon, I want the value to be near 1. If it's an orange, I want the value to be near 0. I would sum that across all my data points. And I would say, OK, I want to minimize this error function. I want to find the settings of p0, p1, and p2 that minimize this function. That really is, like, minimization of some function is basically most of machine learning. OK, so what might that look like? So I might randomly initialize my p0, p1, and p2. So right now, you can see my line is just this random line in the middle of the graph. And then I'm going to make a whole bunch of small changes to p0, p1, and p2 that tend to make the loss function smaller. And the hope is if I do that over and over and over again, eventually I'll find the optimal separating line. So you would get the optimization process would look something like that line slowly shifting to the optimal position. There's all kinds of questions you might have about this. Well, is this always going to work? And how do you decide to update the values of those coefficients, all of those things? I'm not going to really get into that here. One of the answers about is this going to work, why doesn't it get stuck in like some local minimum, is empirically it seems to work for real world problems. That's not a very satisfying answer. There's a whole bunch of people trying to work on why that might be or whether or not we can prove that in certain contexts. But empirically, this very, very simple approach, create a big model of how you want the answer to look like and then wiggle all the parameters of that model until you get the answer, works well assuming that you've set up the right structure of problem. OK. That's a very fast intro to the basic concept of machine learning. This is a concept of supervised learning. You would have to have a data set. Somebody's already told you these are oranges and these are lemons, and you're trying to learn this function to figure out what are oranges and what are lemons. There's other concepts, like there's a thing called unsupervised learning, which I'll talk about a little bit, where it's more I just give you a whole bunch of data and you look for patterns in it without necessarily having labels. There's reinforcement learning. There's other problems. But this is a very common, basic kind of problem. Now, you're going to learn all this. If you take a machine intelligence program, you're going to learn all this. So I don't want to spend too much time on it. But I do want to set a little bit of the context. Because one thing I've noticed, both in myself and in my community in machine learning, is because you can formulate a lot of problems this way, like how do we recognize objects? How do we decide who our friends should be? There's all kinds, you can formulate a lot of things as here's a bunch of examples of my friends, find me more friends. Here's a bunch of examples of products I like, find me more products, whatever. It can start to feel like, oh, all of life fits into this framework. And so there's this big tendency, and this is going to be an opinion that I could be wrong on, but there's this tendency to now say, oh, this is all that the brain is doing, this is all that like life is we've got some loss function. We might not know what it is, but all we're doing is figuring out how to wiggle the weights of our brains to optimize this thing. So it's actually, I think, a strangely controversial opinion that I have in the machine learning community, that intelligence and consciousness in life there isn't a scalar objective that you will ever find that we're optimizing. I think there are sometimes some subtasks that I do that involve optimizing for something. Maybe in EngSci you're trying to optimize for your grades. I don't know. But you're doing that in tension with a whole bunch of other priorities. So as you get deeper and deeper into the math and you've kind of forgotten about the rest of the world, I just want you to every once in a while step back and remember I'm more than just an optimizing machine, because I think that you are. So that said, why do we do machine learning at all? So in the example I gave you earlier of the oranges and lemons, you could just look at that and draw the line for me. You don't necessarily need to do a machine learning process. So some of the reasons that we do it, I mean, there's lots of reasons, but the big one is sometimes defining the function is too hard. So let's say I have this image. This is my cat Meowbot, and I want to know, is this image a cat or a dog? And I want to write a function that's able to take an image and figure out if it's a cat or a dog. This image is just a bunch of pixel values. It's a whole bunch of numbers. So this like corner of the ear, is a bunch of these values, maybe ranging from 0 to 255. So every picture of a cat or a dog that I have is going to be some point in this, hundreds of thousands of dimensional space. Possibly there is some dividing line between cats and dogs in that space. How am I going to find that line? I think in the width and height thing, you could do that by hand. I think here you're going to have a lot of trouble figuring out the magic separator between cats and dogs. And as it turns out, probably that separator is not linear, but is a very complicated nonlinear separator between the cats and the dogs. So this is really where machine learning has come to shine for some of these problems that we know should be solvable, but we don't know how to start writing down the function. Before like the recent successes of deep learning, for instance, these kinds of problems were completely intractable. In early computer vision research, we thought these would be relatively easy because they're very easy for us. It's very easy for me to figure out what's a cat or a dog. It was a big surprise to the community how hard it turned out to be to write a program to do it. In recent years, we've suddenly become pretty good at this task. So that's one case where we kind of know there's a function, we just don't know how to write it. And then there's another case that people like, and this one's a little trickier because you don't know if you're going to ever find an answer. Sometimes people just want to figure out if there is a function. They're like, I bet I could have something that looks at Twitter data and figures out the stock market. I just feel like there's going to be a connection between those things. I don't know what it is. I'm going to get the computer to look at all the data and find that function for me. So there you can set that up as a supervised learning problem. I can get all the Twitter data and I can get all the stock market data and say map A to B. But it's not a given that there is going to be such a mapping or that we'll be able to find it. Okay, so that's kind of why we want things. But again, to reiterate this like responsibility question, things get pretty complicated as we move to the real world. So machine learning is now being used or evaluated in a lot of very important contexts. So insurance and credit decisions, do you apply for a mortgage? Do you get it? Making immigration and refugee decisions. So the Canadian government has put out to tender proposals, and they're likely not using these yet, but they're asking people to come up with AI technologies to make early stage refugee decisions. Maybe that's going to be better, maybe that's going to be worse, but it's certainly it's a place where your responsibility as an engineer is something you should really be thinking about. Making criminal sentencing decisions. This is real now. I'm not sure if in Canada, but in the States, in a lot of judges use algorithms to try to guess whether or not somebody is going to recommit a crime, and they decide whether or not to give them parole on that basis. And this is actually very controversial. I won't talk about it a ton here, but it's been shown that those algorithms are highly discriminatory. Evaluating university and job applications. I mean, I mentioned Amazon earlier, but again, there are real companies today selling products that are used by institutions such as this one. I don't know if this one is using any, that are like looking at people's admissions essays to universities and like having a first pass at which ones are going to like make it through to the human evaluators. This is true of the Amazon AI that they pulled back recently as well. We're driving cars on public roads. Like self-driving cars are powered by a huge amount of this machine learning technology, and they're on the roads today and have been involved in accidents. And like providing therapy. I mean, there's like chatbots that people are starting to put out that we're putting a lot of faith in their ability to like manage or deal with our emotional lives. This is possibly going to be a huge positive thing, giving more people access to this. This could be very negative if the algorithms don't go well. These are very fraught places. So I want to talk about some of the places where issues like bias and discrimination have been shown to come up and possibly will come up again in future. Okay. So with that, I want to talk about an unsupervised learning algorithm called word2vec. So as a field, people have moved on a little bit from this, but this was a work from a few years ago from Google. Basically, this unsupervised learning problem is, I'll just show you a bunch of data and you try to find patterns in it. What they realized is that they could take a huge corpus of just natural text data that's out there, and they could start to learn the semantics of words to some extent. And the way that they did it is they formulated it as, I think that nearby words in a sentence are decent ways of predicting other words in the sentence. So for instance, I'm taking my blank for a walk, you could probably figure out some words that would fit in there. It might be dog, it might be poodle, it might be cat, but other words wouldn't make any sense in there. It wouldn't make sense to put, I'm taking my green for a walk. Probably wouldn't make sense to take my sandwich for a walk, but it's a little bit more plausible. I'm going to eat a blank, maybe that's where a sandwich should go. Joe and blank went to the movies, maybe it's more likely that a name would go in that spot. So if you structure the problem like this, you give it a huge amount of natural text and you just say, predict the missing word from the context. And you have it, you set up your learning problem in such a way as in order to do that, it learns a vector for each word. So it learns, again, a series of numbers, a point in a high-dimensional space that represents each word. Then it turns out, A, we can do a pretty good job of it, and B, those vectors end up capturing a lot of the semantic information about words. And then you can use those for downstream tasks. So you can train them on a huge amount of data, and then for a task where you have a much smaller amount of data, you can start with your representation of words being these vectors, and they encode all this information. They'll know if it's a noun, they'll know if it's an animal, they'll know if it's an adjective, whatever. So that turns out to be a very good pre-training step to feed into subsequent downstream tasks. And what's been really interesting about this is it's been found, and it wasn't designed to do this, but you can actually do plausible vector math with these vectors. And so this is just something people found empirically. So if I take the vector for walked and subtract walking and add swimming, I'll get swam. So there seems to be some subspace, some linear space here that changes things from their, like, what are the grammar words? Anyway, from walking to walked or from swimming to swam. Similarly, you can map capitals to countries. So Madrid minus Spain plus Canada in this space equals Ottawa. This is a very surprising result. It was very interesting. You could also say, so you can start to set up these analogy questions. You can say, man is to woman as king is to queen. So this was interesting as a result we didn't really expect. And then suddenly, especially that last example, people started to ask, okay, well, those are all perfectly fine analogies. What else might be in here? And so some people started to look at, for instance, the associations of professions. And it turns out that if you train something on historical data, it ends up learning these associations. So it ends up learning that man is the computer programmer as woman is the homemaker. And so they found a subspace that was the gender subspace. It was never trained to find this. But in practice, it ended up learning a subspace of data that represented gender. So there's one axis in this high-dimensional space that represents gender. And you can see that the kinds of professions that it put on the extreme she side, it put like homemaker and nurse and receptionist, all these biases, all these stereotypes, which you probably are aware of as stereotypes, but it learned them and they're now baked into its very representation of those words. And similarly, on the male side, you might get maestro and protege and philosopher and captain and all these words that historically have been more male associated in texts that we've written. So why is this happening? I mean, there's lots of discussions about this, but in large part, we're training on huge amounts of historical data going back, like, in some cases, like over 100 years. There have been historical differences in these kinds of professions. If this was just a science question of like, oh, what are biases or what are associations that exist in the corpus of text people have written, this would just be an interesting result, and we'd be like, oh, we've learned that in the corpus of text people have written, this is a fact, this is an association. But if we're learning these vectors and we're using them for downstream tasks to like grade the quality of an essay or to like figure out something on a job application, suddenly having baked into these very vectors this bias becomes potentially problematic. And so this is something that as a field, we don't quite know how to deal with yet. I mean, there's techniques for specifically trying to debias word vectors along the gender axis, but this is still a very open area of research. And what are the consequences of this is also still a big open area of research. So this is one kind of problem that we see. I think another question is who picks the categories? I think we have to remember that this stuff isn't, we talk a lot, we use the term ground truth in machine learning as though like the labels that we have are somehow true and from on high and there's this objectivity to them. And I think it's important to remember that they're not. That, so Kate Crawford says it better than I would, that classification, the set of classes are human constructs. And classification is always a product of its time. And we are in the biggest experimentation of classification in history because at scale with big data, we're trying to build algorithms to classify people. Examples of why classification is always a product of its time, in apartheid era South Africa, they had a number of like officially recognized race categories that you would be sorted into against your will, and they would affect which beaches you were allowed to go to and how many social services you would get, what jobs you were allowed to have. And they would decide on the basis of things like characteristics of people's hair. They had a very famous pencil test where they would stick a pencil in your hair and see how easily it came out. And they would use that to determine whether or not you were allowed to go to certain beaches. And much more significant problems than that. So I can construct this as a machine learning problem. You can give me a labeled data set of these things, a bunch of attributes of people, and I can make an algorithm that's going to start sorting them into these categories. But that's not somehow some truth that has come from the universe just because I use math. It's like, this is still a human construct. And this is there's things to watch out for in the machine learning community. This is quite a controversial paper that came out recently that claimed that it could, with high confidence, predict whether or not someone is likely to commit a crime based on their face. And so they had this data set of government ID photos of people who had committed crimes and hadn't. And then in very, very dubious ways in this paper, they claimed to show that they could predict things with very high confidence. I think we have to ask ourselves, I mean, there's a number of questions we have to ask, but I mean, among other things, do we think the historical sentencing record is somehow fair or unbiased? Do you think that the way that we want to choose how to sentence people in future is just to look at what we did in the past and say, oh, people like this we tend to put in jail, so let's put more people like this in jail? Probably not. So this is a big problem. I would say read this essay. They go into a huge amount of detail on this particular question and all kinds of really interesting social examples. So I think a thing to watch out for, I like Maciej Czeglowski's quote, machine learning is like money laundering for bias. It's a clean mathematical apparatus that gives you the status quo with the aura of logical inevitability. The numbers don't lie. And this is something we see again and again. People start to say, oh, well, it's unbiased. You know, we didn't have a person that was biased making this decision. We had a nice, clean, unbiased computer. I think it's very important to remember that that's just not the case. I think another thing to note, so that's like heavier, like real significant social questions, but it's also just worth pointing out that in general, even with the algorithms we train today, the categories are relatively arbitrary. So the like deep learning revolution was really pushed by results on this particular ImageNet data set called ImageNet, which is a data set of pictures scraped from the internet that are labeled into different categories. So the big breakthrough in around 2012, actually from here at U of T, was Jeff Hinton's group, and they blew the state of the art out of the water for being able to map these images to the class into which they've been categorized. Really interesting result, again, really moved things forward in terms of like object recognition. But these classes, like somebody picked the set of objects that we think are the meaningful set to put here. And as far as I can tell, it's relatively arbitrary. So there's 1,000 categories in this particular subset called ILS-VRC, 1.2 million images that people train on. And then, you know, you got classes like Persian cat and tractor and jack-o'-lantern. For some reason, there's 90 different categories of dogs in the 1,000 classes. So all of these subtle distinctions between Italian greyhounds versus Ibiza hounds versus Great Pyrenees, this is the state-of-the-art. State-of-the-art machine vision systems are often trained on this data set. This one isn't like necessarily a bias problem, but that means these things are spending huge amounts of their representational capacity, their mental capacity, knowing the subtle differences between dog breeds. That's at the expense of something else that they could know. So the choice of categories that we foreground as important totally changes the kinds of problems these algorithms are good at solving. I think this is well articulated by an artist, Constant Dullart, who's Dutch, and he came up with his own data set. He was like, you know, this was created at Stanford and Princeton. I don't know what process it was. It was a couple grad students just made this decision probably. I want to create a Eurocentric data set. So he created Euronet. So it was his own, it followed the same form as ImageNet, but instead all of his classes had a Eurocentric bias. So here we've got the Angela Merkel class, and the mozzarella class, and the blue cheese and the blood sausage class. And these are, actually these images here are a neural network trying to generate what it thinks is the most representative image of that class. So there might be a bit of a way to go for this neural net, because I don't know if that looks like Angela Merkel. But I think this is an important illustration of this point. People will talk in the field about trying to de-bias algorithms or try to make bias-free algorithms. There is no such thing as unbiased data, right? You're always picking some subset of the universe to measure. There's always a set of things that are easier to measure versus harder to measure. There's like, these are photos scraped from the internet. They're things people have chosen to take photos of. This data set might not be appropriate for like a robot that's taking photos from very different angles or very different perspectives. The labeling scheme is always one arbitrary. Labeling schemes, you take all these objects and you decide to categorize them in this particular way. There's other ways you could do that that's not like somehow empirically true. So you will never have unbiased data. You will never have an unbiased algorithm. That's not a problem, but it means that these things are always subject to political critique, and they're always subject to debate, and there's in future things that maybe we didn't think were a problem today will be a problem, and they will always have to be reevaluating these algorithms. We'll never be done. There's no like end state where we have the perfect algorithm. On this point, I just want to emphasize, don't actually listen to me on this. I've had to learn most of these things from much more vocal groups and people who are much more directly impacted by the negative effects of these things. So these warnings that I'm relaying to you, I owe a lot to organizations like Black in AI, Women in Machine Learning, Queer in AI. These are all groups that at the NeurIPS conference, which is like one of the biggest AI conferences, they're very significant groups that are starting to raise some of the issues of discrimination in the field. The AI Now Institute, which is her institute, Kate Crawford, is a really good institute for starting to ask these questions about the social impacts of AI. And I actually highly recommend you watch her keynote from NeurIPS 2017, where she talks in a lot of detail about these kinds of questions. There's a great conference, the Fairness, Accountability, and Transparency Conference, that's asking a lot of these questions. It brings in machine learning engineers, it brings in lawyers, it brings in social scientists to ask these questions. And respect social scientists. You know, the talk yesterday, he did mention that, you know, he wished he'd done more technical things, and that's fair, and I'm totally happy to have done a lot of technical things, but I'm learning so much from the social scientists in my life and from the people who studied philosophy and the people who studied like international relations and politics. And they've learned how to think about these problems in very different ways that I never learned here. One final warning, especially if you're going into this field, it's very new. There's a lot of uncertainty. We don't actually know what's going to be possible and what's not yet. There's certain tasks that we've accomplished pretty well. We're pretty good at machine learning, machine translation, but we don't know how much better it'll get. You know, if you drew a straight line of like how it was 10 years ago to now, you'd be like, oh, we'll be able to do like high quality literary translations in a few years. We actually don't know. Maybe, maybe not. We don't know if chatbots are terrible right now. If you try to talk to an algorithm that talks back to you, there's a lot of hype in chatbot companies, but if you actually talk to a chatbot, it's clearly not an intelligent agent that you're communicating with. Are they going to get much better, or are the current family of techniques going to plateau and that's it? Can we solve this problem of adversarial examples? I didn't really end up talking about that, but a lot of neural nets turn out to seem like they're performing really well, but you can carefully construct inputs that make them output totally ridiculous answers. You can have something that looks exactly like a cat, and it tells you with high confidence it's a toaster because you've added a tiny amount of imperceptible noise to the image. That could be a security problem. That tells us something that we don't understand about what these networks are doing. Will self-driving cars actually be safer? There's a huge narrative out there that these things are much safer because humans die on the roads all the time. But right now, I mean, if we look at like Uber's self-driving car program, they've had one fatality per 3 million miles driven. On average, we have one fatality per 100 million miles on the roads. So it's possible that self-driving cars will be safer, but there's a false narrative being pushed that we know that now. There's a ton we don't yet know in this field. And in general, a lot of people are funding and want AI because they want to know the future. They like, predict my sales in the future, predict when this company will go public, predict the stock market. How much of it is just uncertain? Which things will we be able to predict and which things will we not? To what extent do you have to be careful because somebody will want to hand you money to give them a crystal ball? And is it ethical for you to take that money if you can't in fact give them the crystal ball because it doesn't exist? This is a really ongoing set of questions. Like the field hasn't answered these questions. I think as you go into this field, I think you have to recognize you're going to something with a lot more uncertainty than building a bridge, which isn't to say that building a bridge isn't a very difficult profession, but we kind of know what we're building. We kind of don't know what we're building yet with machine learning. So I think it's a really exciting field, but it's very ambiguous. Okay, I have, I think, about 10 minutes left. I wanted to get into my creative work a little bit because, so I'll blitz through this a little bit, but I wanted to, there's been a lot of like doom and gloom and talking much more about the business applications. But I actually got into computer science through creative work. So I got into it with a programming language called processing, which is designed for visual artists and designers, and I found that a really compelling way as a visual thinker to start to learn about computation. So I've always had that as part of my practice. I think we mentioned off the top, among other things, I've organized an event that's semi-annual called the GenArt Hack Party, where I teach workshops on how to write code to create images, and like we bring together people who've maybe never done code before, and we use this as a way to bring more people into the field. And I want to share, since I've gotten into machine learning more from like straight computer science, I've been playing around a lot with the tools that we can use to make imagery, to make art with machine learning techniques. I'm not the only person doing this. It's a very active community of people doing this kind of work. And I'm going to share a particular technique that I have. I've actually published it at SIGGRAPH Asia, called high resolution multi-scale neural texture synthesis. I'll show you some examples in a minute, but I'll give you a very brief intro to what the idea of this algorithm is. I'm going to take a neural network that's been trained on ImageNet, the dataset I showed you earlier. The intuition is that neural network will consist of a series of layers, and each of those layers will start learning more and more abstracted representations of the exact pixels. So the first layer might just pick out things like edges, things like areas of solid color, things like areas of like slightly more noise. Then a few layers up, I might be detecting slightly higher level concepts. It might be that one particular part of this layer is sensitive to like the eyeballs of the cat, and another part it seems to be sensitive to furry regions, and another region tends to be sensitive to the teeth. And maybe at the highest level, it starts to be very high level concepts like cat or dog. So at a very high level, that's what a lot of computer vision algorithms look like. They look like this series of layers that more and more abstract the input. I think you can kind of think at these higher and higher layers that we've almost changed this thing which started out as just having color at each pixel to having more and more semantic content at each pixel. Suddenly we don't just know red, green, and blue, we know how furry a particular region is and how eyeball-y a particular region is. So then, and this isn't my insight, this is from work from Gaddis. There's this concept of defining the Graham matrix, which is basically going to be how often for a particular image are different features active. So maybe I have a particular image and I could say, I would have this table where some of these high-level features that it's learned, I could say, how often does the furry feature show up near the stripy feature? And maybe they tend, in this particular image, to show up together quite often. Maybe there's a zebra in the image. Maybe the eye feature and the furry feature doesn't show up very often together because there's no regions of the image that have furry eyeballs in them, for instance. So I'm going to feed an image into this network, and I'm going to use this covariance matrix of feature activations to define the textural properties of that image, to define like what things tend to show up together. And then I'm going to run it through an optimization. I'm going to feed in this is a complicated image, but the idea is going to be I feed in the image at multiple scales into this network. For each of those scales, I pull out this covariance matrix, and then I optimize a new image that I try to have match the properties of the source texture. And so this multi-scale property ends up being a very important thing. That's one of my contributions here to create interesting images. So the training process, I feed in maybe some image of a crowd, like that at the top left corner. And then I start with randomly initialized noise. In this case, it's almost imperceptible. I start this optimization process, and then it slowly, over some number of iterations, gets to here, and then a little later it gets to here. And then by the time it's converged, suddenly I have this kind of like believable image of a crowd. But actually, if you look closely, it doesn't really understand what people are, and there's no people in this image. Like, there's kind of just like floating head-like things and shoulder-like things, but it has the textural qualities of a crowd. So I've been using that as a creative material to see what kinds of things I can create. And I've been making images like this based on like images of graffiti around the city, or I've been looking at how I can take these covariance matrices and combine them together to create different kinds of images. So I can like try to combine like the tiled ceilings of mosques with sunflower images and have one textual representation that captures both of these. And now the algorithm tries to create one image that simultaneously has both these textual quantities, and it ends up mixing them together, but in this very like fluid and organic way. I took that concept to the extreme and tried to combine together like 50 different images of streetscapes of Toronto, and I get an image like this, which has it's almost like a collage of the different ways in which Toronto streets look. I showed this in Thailand when I was giving the presentation at SIGGRAPH Asia, and I didn't give very much context to the image, and someone in the audience said, oh, is that Dundas West in Toronto? They somehow picked out the property. I don't know how they did it, but they picked out, and it was a walk I'd taken along Dundas West to photos, and it sort of has the properties of that. I've been playing around with that. This was actually started as a bug, but I'm kind of entertained by it. So I was trying to generate like sort of a berries images, but I screwed up the multi-scale term of my equation. So it ended up trying to have the same statistical properties at every scale of the image. So this ended up being a fractal berries image, where you've got these like strawberries and blackberries and blueberries, but as I zoom in, they're made up of tiny little strawberries and blackberries and blueberries. You can keep going, and it's just like strawberries all the way down. More recently, I've been experimenting. So these are all with target images. I've been experimenting with saying, OK, well, I have this neural network that's able to see all these interesting properties of images. What are the kinds of textures that it knows about? Generate me a set of textures that you think are maximally different, by some definition of maximally different. And I ended up coming up with these really interesting organic textures. So these are just I've just taken a neural network, I've shown it this ImageNet stuff, it's learned about things that differentiate between 90 classes of dogs and jack-o'-lanterns and whatever, and the kinds of textures it turns out to be sensitive to and that it wants to generate, I get these really interesting, like this strange cellular matrix here, and these more like stone-like things at the top left, and these very interesting textures, and they show you a close-up of one, like this looks like a strange burlap to me, but this is just purely hallucinated out of a network that's been trained to do something totally different. So this is telling us something about the kinds of patterns these algorithms come up with. And finally, I've been looking a little bit about how I can take this to animation. So, oops. Oh, it's not going to animate. Oh, bummer. Well, I can't show you. Oh, there we go. So this is trying to take ceramics images and create like fluid, hallucinated animations of those ceramics. This is, again, work in progress to do this at much higher resolution. But these are some of the kinds of things that I've been exploring in my creative practice. All right. I was going to talk a little bit about some other work, artistic work people are doing, but I think I'm out of time. So I'm going to end it there and say I think we have a few minutes for questions still. We have 10 minutes for questions. Perfect. All right. Any questions? That's my cat, by the way. That's Meowbot again. So the question was, do I feel like there's a lot of clash between the creative and technical side of my work, or do I think it works well together? There's definitely a tension. I'm still trying to figure out the best way. I mean, like I have a day job. It takes a lot of my time. It's hard to like do algorithms all day and then do algorithms all night, and so that's definitely a challenge. The mode of thinking, I think, is very different. So that's actually one of the reasons I think it's very important for me to maintain a creative practice, is a reminder that not everything is optimizing some function, where when I am operating in my more like professional context, there tends to be some quantifiable metric that I am able to kind of measure performance on. And what I really find as a very different and difficult mindset as I try to do the more creative work is trying to flex that judgment muscle, trying to make calls where there isn't a right answer, and it's like I have to kind of look into myself and think about where am I trying to get, and is this something that I find compelling? And actually, that part of me is very underdeveloped because I've spent so much time solving analytical questions. So that's a tension, and that's one reason I maintain the practice. So I don't think I think it's compatible with the technical work in that I think it keeps me better balanced to have these other practices. And certainly since I've been doing it in machine learning, it has informed a lot of my understanding of these algorithms. So I think I have a very different intuition about how computer vision systems work for having spent so much time trying to extract weird things out of computer vision systems, as opposed to doing what they were built for. Yeah, for sure. So the comment was the creative work looks a lot like Deep Dream. So yes, absolutely. This technique has some things in common with how Deep Dream worked. Deep Dream has a very similar idea of taking a pre-trained neural network and saying what kinds of patterns is this network sensitive to. And then it tries to amplify those things that it sees. Deep Dream is like basically why I started to see that there were creative potentials with machine learning. Before that, I was doing a lot of this creative work in other contexts. Deep Dream was very influential to me, and also I think kind of kicked off a huge community of people that are doing different kinds of creative work. So this is very much like a child of Deep Dream in some sense. It's building on those ideas. The question is, do I think that machine intelligence is going to lead the next industrial revolution? So first of all, in the spirit of not selling crystal balls that I don't think I can sell, I don't know. I think it's very significant. I think there are a lot of tasks which we couldn't do before, which we can do now. I don't think we know yet what the limit of that is going to be. So I think it's very hard to fully answer that question. I think it's going to be ubiquitous. I think it will, I mean, it already is actually ubiquitous in your life in certain capacities. It's in your smartphones, it's in your shopping, it's in your transportation systems. It's ambiently kind of everywhere. Will it feel like a sea change in the sense, like, will culture be fundamentally different in the way that culture is fundamentally different after the Industrial Revolution? I don't think I have an answer to that. In terms of like this thinking forward, I think there's a lot of things for us to be worried about or conscious of about the power of these things. I tend to be a bit more of a skeptic on the narratives that we're about to unleash some superintelligence onto the world that will transform everything because it like leads us as this like dominant creature. I'm relatively skeptical about those ideas, which are pushed by some people in the community. Yeah.
So my question is, do you think there is much value in learning or like lower level languages like C, for example, as opposed to like learning Python if you're trying to develop different forms of software that incorporate machine learning?
The question was, do we think there's value to doing lower level languages like C as opposed to higher level things like Python if I want to do meaningful work in machine learning? I don't think there's one answer here, and hopefully one theme from the talk is like there's lots of different paths forward. So I actually have done, in the context of machine learning, when I was doing the products I was doing, I wrote a lot of C. And the reason for that was I would train these algorithms with TensorFlow that would train like my emoji predictor, say, with TensorFlow. But in order to get it to run in real time, in memory, on device in a highly compressed way, I had to do a whole bunch of work taking that trained algorithm and finding ways to compress it and finding ways to implement it very, very efficiently at a low level. So for that kind of work, I needed the low-level skills, and I was really happy to have them. But a lot of my colleagues and a lot of people you can do a lot of real research in machine learning at the very high level, and that's especially true now. That wouldn't have been true a few years ago. A lot of the early breakthroughs was before things like TensorFlow and PyTorch existed, and like people would be hacking the GPU on their machine to do computations in ways it was never intended to. I think there'll always be some value in those kinds of skills. But it's not everyone will need to do it. I'll also point out, like I have some friends that are working at companies trying to build the next generation of hardware that will power neural networks in much like lower power and higher efficient ways, more efficient ways. So they have to be looking at a lot of questions of like computer architecture, and they're writing compilers to take neural networks and map them onto totally new hardware. So there's totally meaningful, very low level work you can do that's going to be very significant as well. But all of the stuff I showed there, that was mostly with like Python and high-level stuff. Yeah. Yeah. Yeah, it's you. Yeah.
You mentioned that in machine learning, it's often that stereotypes and biases are kind of baked in because of the data set. So what things do you consider when choosing a data set? And like, where do you gather the data from?
So the question was, I mentioned that there can be stereotypes and bias in data sets, and what kinds of things do you do when choosing a data set? I think that's a really good question. I don't know if I have a great answer for it yet, because in practice, very often, for the problem that you want to tackle, there's not a ton of different options available to you. Especially right now, a lot of these algorithms are very, very data hungry. You need a lot of data. In some future where where the algorithms have gotten to a point where we can handle less data, there might be other options. But sometimes you don't have a ton of choice. Like you might just have to train on Twitter. So when we trained on Twitter, we knew there's like huge amounts of foul content on Twitter, and instead we had to be very mindful. We had to think about our data set. We had to like look at it and understand it and know it, and think about like sources of bias and things that would be in that, and try to come up with strategies to mitigate those. So some of those strategies could be as simple as like blacklists. You can't associate this word with this emoji, things like that. There's newer research into broader questions of, can I train on a data set, but at a high level define some fairness measures or some bias measures for a particular thing that I care about, like say gender bias, and then can I, as part of the training process, regularize or try to make sure that my model starts to ignore that part of its training data. But I don't have an easy answer for you. I think the biggest answer is stop and think about your data, think about where it comes from, and think about if it's actually the thing that you care about. So like if you actually want to predict if somebody's likely to go back to prison, reflect on the fact that your data set is more likely to be people who are convicted of crimes, not people who commit crimes. And those are not necessarily the same thing. And if there's bias in the sentencing procedures and things, those will come into your data set, and that's a thing to at least reflect on and think about ways to mitigate. But I don't really have a great answer. I would check out, there's a project called Data Sheets for Data Sets that I think is from the MIT Media Lab that starts to put forward some ideas about the kinds of questions we should ask about our data sets and the kinds of things you should always ask before approaching one. Yeah, way back there. Yeah.
One of your earlier slides.
So the question was, I said I don't think the main goal of intelligence is optimizing functions. What do I think it is? I mean, honestly, I think this is something where a little bit of, I think the term is epistemic modesty is important. Like, I actually don't know, but I think it's okay to not know, as opposed to being like, well, this is an explanation, I want an explanation, therefore I'm going to latch on to this one. It's more if I reflect on my experience, it seems to me that most of it is not optimizing for something. Like, a lot of these choices that I've made at various points in my career, like, why am I doing this creative work? I don't really know. I want to do it. I find a compulsion to do it. And somebody might argue that it's because I'm actually optimizing for fitness in this way, and it's like evolutionarily important in this other way. I think that's just, I think that's a very reductive and not helpful way to think about yourself. And I think it pigeonholes you into ignoring those parts of yourself that are not that, and only celebrating and only encouraging those parts of yourself that are about competition and maximization and optimization. So I'm not going to answer it because I don't know the answer.
That'll end our discussion.
Great.
So if you want to say any final remarks.
Thank you all for coming. Honestly, this is a huge honor to be here. I give a lot of talks. This was one of the most stressful talks I've given because I feel a lot of responsibility to like young me just not so long ago. So I hope this is helpful. Thanks for coming.